Welcome to this explainer. I am so glad you're here today because we are diving into something truly game-changing: nature's role in sustainable chemistry. We're looking at this amazing and, quite frankly, revolutionary connection between everyday tropical plants, the future of lab synthesis, and how we actually teach these cutting-edge concepts to the next generation. If you've ever wondered how we can make scientific advancements safer for the planet while simultaneously making science education, well, a whole lot less boring, you are absolutely in the right place.
Okay, let's jump right in with a powerful quote directly from our source material that really hits the nail on the head. It reads, "Traditional synthesis can use toxic chemicals, but nature provides a cleaner way. Pandan leaf extract makes synthesis safe and sustainable." For decades, scientific progress has come with a huge environmental price tag, relying on harsh chemicals that literally require hazmat suits to handle. But what if the solution was just growing outside?
So here is our agenda for today. 1. The toxicity problem. 2. Nature's chemistry solution. 3. Making silver from leaves. 4. Teaching the next generation. And 5. The ADDIE education model.
Let's kick things off with Section 1, the toxicity problem.
The contrast here is honestly pretty stark. On one side, we've got traditional synthesis. This relies heavily on toxic, harsh chemicals, the kind that earn a giant skull and crossbones warning label. On the other side, green synthesis completely replaces these hazardous agents with the extract of a super common tropical plant, the pandan leaf. It's a total 180. We're shifting away from dangerous synthetic agents straight over to safe, sustainable, natural solutions.
Moving right along to Section 2, Nature's Chemistry Solution.
Take a look at this complete journey of green synthesis. It starts over on the left with just a freshly crushed pandanus leaf and ends on the right with a microscopic silver nanoparticle, also known as an AGNP. Instead of a lab filled with toxic hazard signs, you get this incredibly natural flowing transformation where plant extracts are doing all the heavy lifting of chemical reduction. It's just an elegant, beautifully efficient process. So you might be asking, why the pandan leaf? Well, it all comes down to phytochemicals, these natural plant compounds. Specifically, things like alkaloids and flavonoids are the hidden heroes here. They act as powerful reduction agents, completely replacing the need for any artificial toxic chemicals. It's kind of like nature built its own fully functioning chemistry set. Which brings us to Section 3, making silver from leaves. Now, this synthesis actually happens in 3 distinct phases. Step 1 is leaf extraction, basically crushing up those leaves to release the phytochemicals we just talked about. Step 2 is the reduction and capping reaction. This is where we introduce a silver nitrate solution so the plant compounds can get to work transforming the silver ions. And finally, Step 3 gives us the resulting AGNPs, yielding a pure silver nucleus stabilized by a natural capping layer that comes straight from the plant itself. No weird chemical stabilizers needed.
And this entire process delivers 3 massive benefits for the future of chemistry. First off, it's totally eco-friendly, removing toxic waste from the equation entirely. Second, it's incredibly cost-effective, utilizing cheap, abundant plants over super expensive synthetics. And critically, it's biocompatible. This means these naturally capped nanoparticles interact safely with biological systems. So it's not just cool science for the sake of it, it is a fundamentally better, greener way to innovate.
But this brings us to a really critical crossroads. Having a revolutionary sustainable chemical process is honestly only half the battle. The other half, that's human. How do we actually go about effectively teaching this complex green nanotechnology to students? Because if the science is getting a modern upgrade, the education definitely needs to be modernized too, right?
Let's explore exactly that in Section 4, teaching the next generation.
Just as toxic chemicals are outdated in the lab, boring, rigid learning methods are totally outdated in the classroom. University educators are actively moving away from traditional, static lectures. They're completely shifting the paradigm to dynamic, highly interactive, digital learning hubs to teach this exact green synthesis process.
Let's break down how they pull this off in Section 5, the ADDIE education model.
The ADDIE model is this chronological, highly structured framework. Step 1 is analysis. Here, educators identified a specific learning gap among undergrads at USM and aligned their goals with Bloom's taxonomy, really focusing on moving students from basic, rote knowledge to actual hands-on application. Step 2 is design, which is mapping out the content into 4 specific topics and creating storyboards. Step 3 is development, literally building the interactive tools. Step 4 is implementation, publishing this resource for the target students. And finally, Step 5 is evaluation, gathering real data to see if the students actually learn the material.
And the educational design truly shines in that development phase. Instead of just handing students a dense, dry textbook that basically doubles as a sleep aid, they built some seriously innovative digital tools. We're talking English comic strips to visualize the science, and interactive activities like matching games, quizzes, and decision trees, built using platforms like Educaplay and Genially. Plus, they hosted the whole shebang on a free Google Sites platform, making it universally accessible. They took complex biochemistry and made it feel intuitive and incredibly interactive.
But hey, a fun tool is only useful if it actually educates, right? In that final evaluation phase, the creators rigorously measured their success. They collected student feedback on usability and engagement using a Likert scale, and they even brought in subject specialists to obtain expert validation and ensure scientific accuracy. This completely guarantees that the digital learning resource actually bridges the gap they identified all the way back in step 1.
We've covered a whole lot of ground today, from the incredible natural reduction power of the pandan leaf to the strategic educational design of the AD model. So I want to leave you with this final thought. If we can replace toxic lab chemicals with common leaves, and we can replace dry lectures with engaging interactive digital models, how might leveraging nature in our chemical labs combined with these modern interactive tools in our classrooms ultimately reshape the future of our entire planet?